Okay, so this should be our shortest video of the day. We're going to talk about modeling exponential growth. We just started graphing exponentials, and we're going to take a look at some actual applications, some real life connections to what we've been doing here. So we've seen formulas kind of looking like this before, in terms of we have a coefficient here, and that's just that's a hard number, and we have here the base of our exponent, base of our power, and the exponent. The exponent t here. Now, exponent. Now we're going to actually take a look at the meaning of these three numbers and then work through just a couple examples, understanding what we can learn from this formula here. So if let's see, so my A value, here, we call the growth factor. And since we're working with exponential growth, the growth factor will always be greater than 1. This B here be the initial population of the subject that we're studying here, and T would be the time elapsed. We know this y here that we're used to seeing on the left side of some of these equations of our functions. This y represents what the population has grown to after a specified amount of time. Now let's take a look. Let's take a look at what I mean here. So bacteria population can be modeled by this equation, where P is population, and T is given to us as the number of days. So what is the initial population of the bacteria? Well, I can take a look at how I've labeled the different parts of this function, and I see that my initial population is given by B. It's given by what's in the brackets here. So my initial population is 2. Now, what would be the population of the bacteria after 8 days? So if it's after 8 days, I know T is the number of days, so T equals 8. And I know my equation is P equals 150 times 2 to the power of T, and here we're going to put to the power of 8. So I can put that into my calculator right away. That's 150 times 2 to the power of 8. And the answer I come out with is 38,400. That is a big number. It's a very big number. But that doesn't mean it's wrong. Exponential functions, they increase very quickly. So this bacteria population began with a population just of 2, and it's become 38,000 after 8 days. So how many days does it take for the bacteria population to reach 153,600? So here, our equation, again, is P equals 150 times 2 to the power of T. Now we're going to solve this through a guess and check method here. Now we know after 8 days, P equals 38,400. So I can make a let's see, a bit of a chart here. Make that a little more vertical. So my population after a certain number of days. So my population is 38,400 after 8 days. So then I can try into my calculator, I can try and put a bigger number than 8 in for t. Let's try 9. So I'll put into my calculator 150 times 2 to the power of 9, and I get 76,800. So for 9 days, I get 76,800 population. That's still not quite big enough. I know I need to get a little bit faster, so let's try after 11 days. Put that into my calculator, and I get 307,200. So I've gone too far. We'll try in the middle and see what number it would have given us. That's 153,600. Perfect. So that's the number we're looking for. Therefore, it takes 10 days to reach this population. And let's take a look at kind of what we covered in our finance topic earlier. So Pam invests a sum of money into an account that earns 5% interest per year. The amount of money in Pam's account is modeled by this equation. So we don't need to come up with the equation like we have when we worked in finance, where t equals the number of years. So how much money did Pam originally invest into the account? Well, I can compare this formula to our formula at the top. Our initial, here we call it initial population. That doesn't mean it's always, the population is a number of organisms. In this case, it's the number of dollars, and it is the initial amount. So the amount of money that Pam originally invested into the account is $2,500. How much money will Pam have after 30 years? So just like above, we're given our t, which is 30 years. And so our equation is the amount equals 2,500 times 1.05 times, to the power of t. And if t equals 30, we're trying to find out what a is. I can just plug that right into my calculator. 2,500 times 1.05 to the power of 30. That's $10,804, 804 and 86 cents. So therefore, Pam will have $10,804.86. And how many years does it take for the investment to reach $8,062.75? Well, I know it takes less than 30 years, that's for sure. What I can do, let's see here, we can set up our table as we did before. I have on the left side my amount of money, and on the right side I have years. So I know after 30 years Pam has 10,804.86. So we can try it by plugging it into our calculator and changing what's in that exponent there. So I'm going to try 25 years because I know it should be less, but not a lot less. After 25 years into my calculator, I get 8,465 and 89 cents there. So I'm still a little bit too high, not a lot too high. I'll try taking one more off, and that's the golden ticket right there. So if t equals 24, then 8062.86 0.75. Therefore, it takes 24 years. So what I was putting into my calculator here was A equals 2,500, it was 1.05, and then I changed the number. So for the last problem I put 30 in, and then when I was checking I put 25, and then to find the answer I put 24. So I found out that that equals 8,062.75. That's how I did it. If you have any questions, you know what to do. This should give you an idea of how exponential growth works and how quickly it can increase.